Hi folks, it's Mr. Moodlage here with another video. This time we're looking at lesson number 31, rational word problems. So today we're going to look at 3 rational word problems together, example 1, 2, and 3. And these problems can feel frustrating at first, but I want to assure you that they become easier when you stay organized and focus on the meaning of the problem, of the situation, rather than just rushing into the algebra. Okay, so the big idea for today is rational word problems are usually not about fancy algebra at first, but they're about choosing the right relationship. So for example, for these kinds of questions, I want you to follow this process. And I'll actually write this process down here, just so it's like a little bit easier for you. But the idea is this. So I'll call this like a six-step process for, I don't know, like solving rational word problems. Feel free to write this in the back of your page, the back side, as you see fit. Okay, 6-step process for following rational word problems. Number 1 is define your variable clearly. Define your variable clearly. Okay, number 2 is going to be decide what formula or relationship fits the situation, right? Decide what formula or relationship fits the situation. Situation. Number 3 is, I'll leave some space here actually. I'll come back to that. Number 3 is to organize that information. So organize the information. Here, sometimes a table can be helpful. That's an optional step though. Okay. Number 4 is to build the equation carefully. Build the equation carefully. Okay, and then number 5, after you have the equation, you want to solve the equation. And then number 6, you want to check your answer to see if it makes sense in the context, right? So number 6 is kind of like state the answer and also check. And just do a quick check. Check if your answer makes sense in the context of the problem. Right? Okay. And also, just a little bit of a preamble here, when we say solving rational word problems, right? We see these rational equations come up. It usually means we're dividing. Okay, so the reason we have rational problems comes from the dividing. Also, I'll put that in quotes. Dividing nature of the problem. Okay, so that's where like these rational equations come from. Okay, so for example, and this is what the point I was making here is decide what formula relationship to use to fit the situation. Well, for example, we know from things that we see in real life. We know things like, for example, we can have the units kilometers per hour, right? That's a speed. That's a speed. And I can clearly see here that kilometers is a distance. Let's call that d. Hours is a time, right? So I can get the formula. I can get this relationship where s for speed is distance over time, right? And from this, I can extract other variants of this formula. Like if I were to, swap the s and the t, I could get time is equal to distance over speed. So that is like a very common scenario type of problem that we'll see relating to time, distance, and speed, right? Another type of relationship that comes up a lot is when we have cost per person. So I'll write that here. For example, cost per person. So things like shared cost per person is equal to total cost divided by number of people. Right? That's another way that these kinds of rational equations can show up in these types of problems. Okay, so let's just go through the examples very carefully, and we'll see how this fits into the bigger picture. Okay, all right. So starting with example number 1. So let's read the problem first. So here I have Shalini can run 3 miles per hour faster than her sister Mina can walk. If Shalini ran 12 miles in the same time it took Mina to walk 8 miles, what is the speed of each sister in this case? And we have a table here that's given to help us organize the information. But let's just slow down before jumping into the algebra and ask ourselves what the key idea is here, right? So the key phrase and the thing that I want you to lock in on is this thing right here, in the same time. In the same time. So that is the key word. This means that the times are equal. The times are equal. Essentially, I'm going to create an equation and set those two times equal to each other. So that's where the problem, the thinking comes in with these word problems. Okay, so this is clearly not a problem where the distances are equal. The distances are not supposed to be equal because one person goes 12 miles and the other goes 8 miles. Clearly, we could see that the distances are not equal, right? One is going 12, the other is going 8. So the thing that stays the same is the time, right? Okay, so now let's define our variable. All right, in this problem, the best variable to use is to say let x equal Mina's speed. Mina's speed. Right? Because we could see that since Shalini runs 3 miles per hour faster than Shalini's speed, so if we call, let me just label this table here. So Mina's speed is going to be x, then clearly Shalini's speed is going to be, since Shalini runs 3 miles faster, Shalini's speed is going to be x plus 3, right? According to the problem, Shalini can run 3 miles per hour faster than Mina can walk. So Mina's slower, I'll call her x, and then Shalini is going to be x plus 3. I hope that makes sense, where x is the speed here, okay? Nice. So now let's use our formula. Oh, by the way, I know the distances as well. I could label that, fill that in as right here as well. If Shalini ran 12 miles, so Shalini ran 12 miles, and then it, in the same time, sure, Mina walks 8 miles. All right. Now I can make use of that equation. I can make use of this equation. It comes from, I will write this right here. We know that speed is equal to distance over time, right? Things like kilometers per hour is just kilometers divided by hours, right? That's just how that works. That's speed, and this is distance, and this is time. That's the best way to remember that, right? And so I can say that time then, if I just rearrange that, is equal to distance divided by speed. And then for each person here, so for Mina's time is going to be the distance 12 divided by this time. So 12 over x plus 3. That's going to be Shalini's time rather. And then for Mina, the slower person, Mina, her time is going to be this distance, 8, divided by this speed of x right here. Okay? And there you go. So that's Shalini's and Mina's times respectively. Since the times are equal now, and this is this is like step, if we go back here, this is, so I've organized the information. This is building the equation now. This is like step 4. I can set the two times equal to each other since the times are equal, right? So I can write this now. I can write 8, so let's say, sure, I'll say Mina's time is equal to Shalini's time, so 8 over x is equal to 12 over x plus 3, right? Because the times are equal. Okay, so now it's time to solve this. I can cross multiply, right? That's the trick that we know how to deal with when we have fractional equations like this. So I can write x times x plus 3, remember don't forget to put the brackets there, is equal to 12 times x. Okay, now I can expand this, so 8x plus 24 is equal to 12x. I can subtract x from both sides to get 24 is equal to 4x. And then dividing by 4 both sides, I get x is equal to 6. Okay, so I will conclude, therefore, Mina's, let me rearrange that, Mina's speed is 6 miles per hour. Okay, and then Shalini's speed, and Shalini's speed is 6 plus 3, right? X plus 3, so 9 miles per hour. Okay, and that's my answer. And by the way, it's a good idea to always check this. So let's just check it quickly. Mina's time was, Mina's time right here was 8 divided by x, which we got as 6. So her time, I'll write it right here. Her time comes out to 8 divided by 6, which reduces to 4 over 3. Sure, that's her time. In hours, how long it took for her to walk that distance at that speed. And then for Shalini, her time was 12 divided by x plus 3, which was 9. This also reduces to 4 over 3. So the times are the same, which does confirm it's perfect. It makes sense. Right here, I just want to comment right here, when we did the cross multiplication, you might be wondering, where does that come in and why can we just cross multiply like that? Well, just a little bit of a side note here. The reason for that is because, remember, when we're solving equations, rational equations, we want to make sure that we have a common denominator, right? In order for us to equate the numerators. So that just means that, the common denominator between these two is an x times an x plus 3. So I multiply this thing by x plus 3, both the top and the bottom, right? And then this one, this entire fraction by x. Now notice that the denominators are now the same. X plus 3 times x, x plus 3 times x. So when I have a situation where two fractions where the denominators are the same, left side equals right side, I can say that now the numerators are the same. So I literally get what I'd get as if I'd cross multiplied. So 8x plus 3 is equal to 12x, right? In case you didn't see that, that's why we were allowed to cross multiply like that. Okay, so we've just solved that problem and we're good there. Okay, sounds good. And just a very common mistake that we see for this type of problem is, mixing up who's faster. Just be careful, right? If Mina is walking and Shalini is running, then Shalini must be the one with the x plus 3, right? It's not the other way around. And when the problem says same time, set the time expressions equal to each other, just like we did here. Okay, so that's that problem fully solved. Okay, let's move on to number 2 here. So for number 2, we have, so let's read the problem together. The time it takes for a canoe to go 3 kilometers upstream and back 3 kilometers downstream is 4 hours. The current in the lake, so the speed of the water in the lake, is 1 kilometer per hour. Find the average speed of the canoe in still water. Okay, so this is a classic current problem. The important idea that I want you to realize for this one is this, right? This is what you need to really understand in order to solve this, that upstream, so this idea of upstream is slower and downstream is faster. Why? Because you're going with the current. Upstream, you're going against the current. So when you go upstream, the water is working against you. When you go downstream, the water helps you. Okay, so that's the idea that you want to get across here. So let's define our variable. In this problem, let's let x, I generally like to use the variable x. That's okay, you could use any letter, but let x equal speed of the canoe in still water, right? Then we can compare this with upstream and downstream. So let x equal speed of canoe in still water. Okay, so the current is 1 kilometer per hour, right? So the upstream, and there we have it labeled right here, the upstream speed, meaning against the current, is going to be x minus 1, because it's slower, right? Remember, x is just the speed as if there were no current. And if there is a current upstream, it's going to be x minus 1. Downstream, the current downstream is going to help us. We're going to go faster, right? Our base speed plus the current speed is going to be x plus 1. So that's our speed right there. Now, again, similar to the previous problem, here we're going to make use of that time divided by distance equation, right? We're going to make use of that time is equal to distance divided by speed equation. Because, and the reason for this is because they both travel the same distance, right? The distance is the same, 3 kilometers to go upstream, 3 kilometers to go downstream. So I can, without any doubt, put 3 kilometers in each there. And now I know that the time, right, recall, the upstream time is just going to be, so I'll write that here again, recall time is equal to distance divided by speed, right? The time it takes for anything is always going to be the distance that it has to cover divided by how fast is it going. So that'll give us the time, right? So I can take this distance 3, that distance there, and divide it by x minus 1 to get the time that it takes for the canoe to travel upstream, okay, against the current. And then for downstream, it'll be faster. It's going to be x divided by, 3 divided by x plus 1. So the time will get shorter, right? So, yeah, nice. So now the question here is, what do we do with these two times, right? We know that the times are not equal. Clearly, they're not, one's faster or one's slower, right? But the problem says here, and this is the key part, the time is 4 hours. So total time, so I can use that now, total time equals 4 hours. So I use that for to come up with the equation here. So we just add the times, 3, that expression and this expression, right? So if I add them, 3 over x minus 1 plus 3 over x plus 1 is going to equal 4 hours, right? The time that it takes the canoe to go down upstream and then downstream is going to be 4 hours. And I've just figured out what those times are right there. Okay, all right. So now we solve. And this is where it becomes like a rational, solving a rational equation type problem, right? So we want to use a common denominator. Remember, there's like an imaginary 1 here. My common denominator here is going to be x minus 1 times x plus 1. That's my lowest common denominator. So I will just write it like this. X minus 1, x plus 1, right? And then I will put a line here. I'm going to see how many times does x minus 1 go into this one. Well, it's x plus 1 times. So then I multiply the denominator x by x plus 1 and the numerator by x plus 1. So I'm going to get 3 times x plus 1 like that. and then plus now on to the next fraction. There was already an x plus 1. I need to get an x minus 1 there. So I multiplied both the top and bottom by x minus 1. So I'm going to write the 3, put a bracket here and write x minus 1, or sorry, minus 1, like that. And then I'm going to set that equal to here. I want the denominator x minus 1, x plus 1. So I just multiply the numerator, which was like, or sorry, the denominator, which was 1, became now x minus 1, x plus 1. So I have to multiply the numerator by that exact thing. So it's going to be 4, and then x minus 1, x plus 1. And since now, when I get to this stage, notice that the denominators on both sides are equal, so I can set the numerators equal to each other. So I just, essentially doing this, I get rid of the denominators. That's the whole point of this, right? And one other thing that I want to mention for this, folks, is that, well, clearly we could see restrictions here, right? For these problems, it's like, since it's a word problem, I'm only asking you for what the actual answer is. We're not really concerned about, what it can't be, because there's only one scenario what it can equal, right? There's only one inherent answer here. But for stuff like this, like you're going to see, well, yeah, x cannot be 1, x cannot be negative 1, can't have negative speeds, right? That's not going to make sense in the context here. And we also, like a speed of anything, like if it's equal to 1, then that's not going to make sense either in this case, because then you'd get like you'd be dividing by 0, the time wouldn't make sense. So we'll keep going through this, and then we'll kind of see what the answer gives us, and we'll check to see if that makes sense. So it's always go through the problem and then check, right? If this was just a general problem with no context, then we would have to state restrictions. I hope that makes sense. Okay, so moving on here, I can now state that the numerators are equal. So I get 3x plus 1 plus 3x minus 1 has to equal 4x minus 1, x plus 1. Okay, so I get like that. Now I can clearly, I want to like get everything onto one side, because I want to expand everything, I should say, and then get everything to one side, because this is gonna look like a quadratic equation here. So I'm gonna get 3x plus 3 plus 3x minus 3. Remember, I'm distributing the 3, right? And don't forget the negative there. And then this is gonna be 4. This is gonna be x squared minus 1, right? It's a difference of squares, so it's just x squared minus 1 there when I expand that. Or if, in other words, if I factored that, I'd get this, right? So that's how I know it looks like that. Nice. And I will write this. So here, some things cancel out, positive 3 and negative 3. And then I would get 6x is equal to 4x squared minus 4. I'll bring everything to one side. So I'll actually move this to this side. So subtract 6x from both sides. And I'll get, I'll write the 4x squared first. So 4x squared minus 6x minus 4 is equal to 0, right? If you subtract 6x from both sides, you'll get this. And then this side will just be equal to 0. I can also just simplify this by dividing both sides by 2. So I get 2x squared minus 3x minus 2 is equal to 0. Let me see if this is factorable. It probably is. It does look like it could be factored, so I'll kind of like do this here. And it's going to be like man with a twist, I believe, right? So two numbers that multiply to negative 4 add to negative 3. How about negative 2 and how about negative 4 and 1? I think that could work, yes. So my numbers, n, I'll do negative 4 comma 1. Yep, that could work. I just need to make sure to divide by the a factor here, the a value here. So divide by 2, divide by 2. So this is going to be negative 2 over 1. And then this is going to be 1 over 2. Stays the same. Remember, the bottom, the denominator is what carries the x, right? That's what I have to put in front of the x, that number. So essentially, this is going to look like this once I factored this, right? Once I factored it, it's going to look like 1x or x minus 2, and then 2x plus 1, right? And this is going to equal 0, so I factored that. Sorry for the space, but I'm going to continue here. It's a little bit crazy there in terms of spacing, but okay, so actually, no, I can do it here. I want to make use of the 0 property now. So when is this thing going to equal 0? It's when x is equal to a negative half. When is this thing going to equal 0? It's when x is equal to 2. This clearly is inadmissible. We reject that because if we think about the context, the speed, right? X is the speed of the canoe in still water. The speed cannot be negative here. So we reject this, right? And we just say that I want to erase it, but I want to reject this because speed cannot be negative. So I'll say reject. Can't have negative speeds here. So the speed of the canoe in still water is going to be 2. I will just conclude this right over here by saying find the average speed of the canoe in still water. Therefore, I'll say the speed of the canoe in still water is 2 kilometers per hour, right? Our units were kilometers per hour, so that is going to be our speed. That's the value of x here. And again, once we've gotten this, it's generally a very good idea to check. So if the canoe is going 2 kilometers in still water, so right here, right, it's going 2 kilometers in still water, then the upstream speed is going to be 2 minus 1, which is going to be 1 kilometer per hour. And the downstream speed is going to be 2 plus 1, so 3 kilometers per hour. And the upstream time, so clearly, right, downstream is faster, upstream is slower. The upstream time is going to be 3 divided by 1, so it's just 3 hours. So this is going to be 3 hours. It's going to take 3 hours to go upstream. And then this is going to be 3 divided by 3, which is 1. So it's going to take 1 hour to go downstream, which makes sense. It's going faster, right? So the total time here, the 3 hours plus the 1 hour is 4 hours, right? Which is what the question says, 4 hours. So it checks out, so it works. Okay, so another thing, so it checks out perfect. Remember, when the problem says, in this case, total time, so this 4 hours total, so like to go upstream and downstream, that's total, we add the time expressions as we did here, right? We add them. Another key point here is for upstream, downstream type questions, against the current means subtract, right? Against or upstream means subtract to get the speed. When the current, with the current, so downstream, we add, okay? Common mistakes in this problem for these types of word problems, rational word problems, is students often reverse the signs and write upstream as, x plus 1, but that would be wrong. It has to be x minus 1. That would make no physical sense because going upstream should be slower, not faster, right? And also, like I would mention a restriction here as well. Since the upstream speed is x minus 1, we know that x has to be greater than 1, right? Clearly, like if we put any value of x here that is less than 1, we would get negative speeds, which doesn't make sense. So x has to be bigger than 1, at least 1, right? Or it can't even be 1 because then the speed would be 0. It has to be greater than 1, okay? All right, so that's it for that example. We can now move on to number 3. All right. So let's read this problem right here, this last one right here. It says here, a group of girls decided to go on a trip to the beach and the organizer said that the bus would cost $360 to rent, okay, for that group. The organizer also told them that if they got 3 more girls to go on the trip, each girl would pay $6 less, which they ended up doing. So like the more people go, the less, right, per person. How many girls ended up going on the trip? That is the question. Interesting. Okay, so this is what we call, this type of problem, this is a shared cost problem. So this is a shared cost problem. Okay, so the important thing that stays the same is the total bus cost, right? So total bus cost, the $360 is, no matter how many girls go, it's gonna cost total 360, right? The thing that will change, what changes, is the number of girls. And because of that, the cost per girl changes, right? So the more people go, the cost that one person pays will be less, but overall, you still have to cover that 360, right? It's total. Okay, so now let's define our variable. So here we can say let x equal original number of girls. Original number of girls, right, that we're planning to go. So the original cost per girl, so then I will write, here I'm going to actually organize my information using bullet points as opposed to a table, but just showing you the different ways that you can organize it, right? So then the original cost per girl, then the original cost per girl, right? This was before the 3 additional girls were added, is going to be the total cost, which is 360 divided by x. Makes sense, right? If 3 more girls go, if 3 more girls go, then the new number of girls will be x, which is the old number, plus 3, right? Just 3 more. That's why we call the original number x. This is a smaller one, so then you make use of addition to come up with the new one, right? X plus 3 as an expression. So the new cost, the new cost per girl is 360 divided by the total number of new girls, right? So, I mean, including everybody. So it's going to be x plus 3, right? Because it's total cost divided by the total number of actual people now. So now the problem says, and this is where it gets interesting, right? So this is what the equation says now. I want to make use of these. So the problem says that new cost is going to equal old cost minus 6. Okay, so this means that, if that's what that means, right? So the new cost is going to be like new cost per girl, right? So it's going to be 360 divided by x plus 3. That's going to be the new cost per girl is going to be the old cost 360 divided by x minus 6. And that is my equation, right? So the problem says that with 3 more girls, that's the cost per girl now, is going to be the original cost, had there been 3 less, per girl minus 6. So it'd be $6 less. And that's what that means. So now we solve. Now we've done the full thinking here. Now it's just a matter of solving. Here, the common denominator is going to be, so there's an imaginary 1 here. The common denominator is going to be x times x plus 3. So I multiply both sides by x times x plus 3. You could take a look at the previous example, but in doing so, I would get something like this, right? So multiplying both sides by x times x plus 3, right? So this is what I'm doing. And I can do this I'm approaching this another way, right? It's the same idea, finding a common denominator and then equating to the numerator once you find that. But this is also the reason why that works is because, the logic there works too, but in math, if I have an equation, what I do to the left side, as long as I do it to the right side, I get the same thing. So I'm going to multiply both sides by this, x times x plus 3. Multiply this side by x times x plus 3. Here you just got to be careful because that x times x plus 3, that entire thing that I'm multiplying goes into each one, right? So not just the last one or the first one, but it's literally like, maybe it makes sense if I wrote it like this. So this thing this thing is getting multiplied by x times x plus 3. And then this thing is getting timesed, I'll say right here, timesed by x times x plus 3. Right? And now you're going to see that there's just a bunch of things being multiplied, and you're going to get things crossing off, right? X plus 3 here and x plus 3 here. So on the left side, I'm going to get 360 times x, right? Notice how efficient this is, right? On this one here, I have an x canceling with an x here. It's just the same as the last problem, but instead of finding a common denominator, I'm just multiplying both sides. So I can do that too. I can find a common denominator like we did the first one here, or I can just do what I'm doing here, and it still works both ways. I could have done this the other way. I could have done that this way, right? So I'm showing you different ways of solving it. You can pick and choose which way you like, right? So I get 360 times x plus 3. And then lastly, I have minus 6. There's nothing crossing off from the bottom. This is at the top, by the way, right? Because it's a 1. So I just literally have to rewrite this. Minus 6 times x plus 3. All right, so that gets rewritten just like that. And then we are good here. And now I'm going to expand this, right? So I'm going to write 360x is equal to 360x plus that one is going to be 360 times 3 is going to be 1080 minus 6, and I'll put bracket here. That's going to be x squared plus 3x, x squared plus 3x. Okay, so expand that. That's going to be 360x equals to 360x plus 1080 minus 6x squared minus 18x. So I just expanded everything. Now I'm going to there's stuff that cancels from both sides. So 360x and 360x, they disappear, and I get something like this. So I'm going to bring everything to the other side, make this positive, right? So add 6x squared to both sides. So I get 6x squared on the left side now. Add 18x, so plus 18x, and subtract 1080 from the right side and the left side. So 1080 is equal to 0 now. Okay, I'm going to divide both everything by 6. I know that they're all divisible by 6, believe it or not. There's all factors of 6. And I would get this. So dividing by 6, I get x squared plus 3x minus 180. And I quickly just check this. 1080 divided by 6 is 180. Yes, that does work out. Okay, good. So now it turns out that this is factorable. Man, if you work this out, the two factors are going to be x plus 15 and x minus 12. Maybe you didn't know that. If you didn't know that, then you could always just use the quadratic formula, set this equal to 0. And now it's just I'm using the 0 property, right? So x is going to equal negative 15, and x is going to equal 12. Here, I reject this, right? I can't have a negative number of people, so reject that. And I just end up with this right here. So x is equal to 12. Now, be careful here, right? The question is not asking for the original number of girls. That's where you have to be careful. It asks how many girls ended up going on the trip, right? So I'll highlight that right here. It says how many girls ended up going on the trip, right? So it's a common mistake, right? So the original number of 12, 3 more went, right? So 12 plus 3 is equal to 15. So the final answer is therefore 15 girls went on the trip. That's the answer that you're after. Okay, and that's all. Again, always check what the question's asking. Sometimes your variable is not the final answer, right? Here, like it's not the final answer in this case. Your variable can, like we did here, like it represents the original amount. So the question asks for the new amount. So you want to go back and make sure to calculate that as we did here. So a common mistake is stopping at the 12. This would be the original number, not the number that we're actually ended up going. All right. Just a little bit of a summary recap here. Example 1 was all about the same time, that kind of thing. Tells us to set the two time expressions equal to each other and then solve. In example 2, we're looking at total time. So we add the time expressions here like we did. And example 3, it says that the total cost stays fixed, right? So the total cost stays fixed right here. The 360 stays fixed. So we compare the two cost per person expressions, right? So here, this cost per person, new cost per person, old cost per person, the difference is 6. And that's that. So if a rational word problem feels hard, just remember that the hardest part is not the algebra. It's figuring out what the the relationship that the story is trying to describe, right? So you got to ask yourself, what's staying the same? What's changing? Am I comparing times? Am I adding times? Am I comparing cost per person? If you can answer those questions, then the equation becomes much easier to build, right? And once the equation is built correctly, the algebra is usually the easier part. And there's, as you can see here, there's many ways that we can come up to the same equation, to the same final answer. So take your time, stay organized, don't panic. If it doesn't click immediately, these problems get much easier and much better with practice, right? Speaking of practice, here's the homework for this lesson. I want you to complete these problems. The answers are here, but work them out step by step like this and see if you can also get to those answers. Okay? Thank you and have a great day.